Hello, everyone. As Michael already said, I think I'm from a company, actually a startup, which has a revenue of less than $1 billion here. So it's nice to be here. Before I start, I'd like to actually give you a little background. Probably I've been involved in the Eclipse Foundation longer than everyone else here. Since its very first days, in 2004, after the first Eclipse project came out, which was the Java tooling, that IDE, which gave probably Eclipse one of its first big exposures. Again, I was with another initiative. We were building enterprise tooling. So I'm a tools guy. And this tool displaced one of the biggest names in that time, which was the IBM WebSphere tooling, WebSphere Application Studio. And then we came together with IBM and our little tool, and we created the Eclipse Web Tools Platform project, which became a highly successful and still ongoing project today, which should give you an idea the type of environment Eclipse provides. It really gives you a platform where little guys like us and the big names in the industry can come together, and you shouldn't be scared of them. You shouldn't be scared of Microsoft or Bosch or Continental if you're from a little company. You can get in there. You don't have to have the right idea. You can be as mad and as stupid as you want. And good things come out of that. That is really important. That's what we learned. And then I moved on. I did a lot of things on the enterprise space. I worked for very big companies. Then I started my own company. Again, we moved into cloud-native space, and as with the technology, we moved on to IoT. And when you're from a small company, you do a lot of pivots. You have to move on, you have to make quick decisions, and which took us through some chance and encounters with customers, brought us into the automotive space. And the whole idea was that when we were working with them, we worked with some robotics applications and unmanned vehicles and some autonomous vehicles. And all of these things have predominantly have ROS stacks, so the robotic operating system. And the algorithms and the nodes on these machines are typically trained for very specific environments. They can move in this room, they can move in a campus, maybe they can go around in San Francisco. If you take them out and you put them, for example, in a city like Istanbul, they'll do nothing. They'll probably crash into the first wall. And well, that's not a problem for most of these guys, but then you work with very small robots, and they are good in this room, but you open the door, they get out of the room. And what do you do? And so we were looking at, well, how can we deploy software onto these environments that can switch with the environment that they're in? Because we already know what works in that environment. Can we switch it while this robot is running? So it's some ways not very different than LIDA. We're creating a deployment, but we have to do it while it's running. And we have to make sure that it doesn't run onto the wall. And we have to do it very fast. So that was the whole idea with this adaptive stack that we came up with. Then as you're building, you realize that lots of people do things very differently. So you cannot really generalize the models. You cannot generalize the ontologies or metadata. Everyone has their own. So what can you generalize out of this? So how can we make this extensible? And out of these, we came up with a few components that we thought were very useful, and that we thought that coming into Eclipse and Eclipse Automotive, we can work with companies which can give us different ideas and how to build these into other systems. That was the birth of Eclipse Muto. Andy was here a while ago, but anyway, so we started looking around in Eclipse because we knew Eclipse, how it worked. We thought that was the right place. So we became a part of OpenADX first. And then when Eclipse SDV came, which is a code-first approach, we said, there's something concrete. This is where where we can give some code, and then we can meet people who are actually writing code, and we can see how we can use what they're doing. We can use what environments they're using. how can we make this be used in different places so that we grow as a company, our product grows as a company, we also contribute back. So that's the whole thing about Eclipse Muto and this word adaptive there, and I'd like to give you a little bit of the background. Our project leader, the actual guys who developed the software, I still write code day in, day out, but they are the real guys. He is online now. Hopefully, if you ask me really hard questions, he'll be able to maybe give you the answer, Michael, on the chat. Then I can work with that. So Dennis is not here today. So let me try this clicker. I was so pumped to say, Alexa, next slide, but it's not going to happen, I guess. So. There we go. So, as I said, Eclipse Muto, actually we start with our company logo is a chameleon, so we thought, oh, let's call it Eclipse Chameleon, but apparently there were issues with that one. So after looking around, unfortunately, Christine's not as sexy as Lida, so we came with some kind of a, something from a different part of the animal kingdom. we chose sort of something that mutates, a Muto, but then we started kind of liking the name now. So that's another one of the things. So these are some of the components that we thought each one of them can be used separately, and I'll get into the details, but together they can be used as a scaffolding to build these adaptive ROS stacks. Basically, I want to oversimplify everything that is in there now. You can think of this as a very smart launcher. If you work with ROS, you know what that is. In ROS, these are XML files that you can just, as long as the software is installed there, you can just say, run my system. So it's basically a manifest. It's a little similar to the Kubernetes manifest in terms of deployment. So it brings up the system, okay? But what Muto does is, there's a model, a bit like the Kubernetes manifest, built from a very simplified version of a ROS stack. Again, it's a YAML JSON-based model, and when you send it to the agent, it works with a asynchronous bus. The composer picks it up, and then looks at what's running on the device, and does some constraint programming, does some validation, and does some graph rewriting to decide what should be killed, what should be restarted. So basically, readapts what's running on the machine. Of course, sometimes you cannot stop that robot. Like, imagine if this was a car. Hopefully someone will not use this on a car for a long time, but if you were using this on a car, if it was an autonomous car, you can imagine the navigation model stopping and something else stopping, and what happens in that little period. Maybe you have to park the car while this is happening. But we have a use case. This is a real use case. Imagine that you have these cars, maybe you're driving it, but you get to the airport and you go into the parking lot. You don't want to look for a parking spot. Let the parking lot control your car. Just drop your car, and if these two systems are compatible with each other, they are robots, and my car should be able to pull the software stack coming from the infrastructure, let the car be driven remotely or automatically in that parking lot, and I just walk to the terminal. So in order to do that, you have to teach every car, every parking lot in the whole world. But why should I do that? If the system and the certified parts of that system is able to switch this model, then I should be able to do it. So that's the whole idea of the Eclipse Mutos. I'm still trying to get used to the name, Eclipse Muto. So that's the whole thing about the adaptiveness. So the agent is basically, I'll get into those details because there are parts of it. So we also tried to build some, this was for our own use, especially when we're developing, we want to use something that can run in test environments, kind of scaled down. We were looking at, again, other open source stacks which uses ROS And for autonomous driving, one of them is AutoWare, especially the new AutoWare that uses ROS2. The other one is the F1 tent. Again, this is an educational environment. I don't know if you're familiar with the F1 tent racing. Universities gather every year, and they use this platform to test their algorithms to go around on a circle. But one of the things, I don't know if you ever watched them, basically off the line, these are circles which almost like cardboard-like this environments that cars run really fast inside. It's a bit like the Indy, but smaller scale. But you can sort of kick one of the cardboards and the car will fly out of the thing. So we said, what if I kick the cardboard on purpose and the car can switch from running on that track into going into this unstructured environment and maybe switch to some different algorithm while it's doing that. So that's the F1 tent sandbox that we're using. Basically, we reverse engineer the ROS stacks they have and build those models and see how it can work. Then we also have a dashboard. This is a web-based dashboard, but it can be done as it basically can be used as a remote control module, or it can also be used for telemetry. And it also works with the Ditto digital twins engine. So while we were building this dashboard, because everything we do is so specific that we did not want to hard code things into it, we built a framework. This is basically a micro front-end framework that, again, we wanted that to change while it's running. So we did not want to statically compile and run something, so we built this. That was the live UI part. Muto will also be contributing to that framework. It's a JavaScript-based framework, but it works with both web frameworks and also it can be built as a React Native thing, so it can build into Android Auto and CarPlay using some extra framework. So that is the bits and pieces of what Eclipse Muto is, and each one of these blue components, the ones on top are basically, they require ROS. So they are Muto Agent and Muto Composer. It runs on the edge device or the robot. It requires an environment capable of executing ROS engine. So if you're wondering how much resource it requires, it depends on what you're building. As long as ROS runs, both Composer and Agent are very lightweight. That was another one of our design decisions. Maybe I'm talking too much to the slides. I should move on. Okay. So anyway, so one of the design decisions we had was the word model-driven gives me queasy sometimes because I think the sort of top-down approaches, you build something that generates code and it runs. I've been in software industry for 35 years. I have never seen that work very well. Over the years, especially it gets so over-engineered that people hate it. I think I've heard some examples from. I apologize, I don't understand AutoSAR. I'm very ignorant to that spec, but I've been hearing things like, the XML is so complex, right? So if you're trying to model that from top, it becomes probably a painful process. Not that it doesn't work, it just becomes. So we did not want to make something that is very heavily engineered, be as lightweight as possible, be practical. So all of these pieces are really fairly simple. As I said, if you're going to deploy a stack onto an edge device, you have to do a lot of things. You have to first, for example, is this stack going to run on that edge device? So you have to validate it. So in order to validate, you just think, you probably know about ROS better than I do, but each component has some system dependency, plus it also depends on other nodes. So when you have that kind of stuff, so you have some technical packaging problems that you have to make sure that you can validate and activate on that device. So if you send a stack and it doesn't match, you can't do anything. So you have to capture a lot of that in some metadata, and as I said, these can be formed into constraints on how, what devices can run or what modules can work with each other, but they all require some kind of an ontology. We did not want to build another ontology for autonomous driving, so we said it should be flexible enough and extensible enough that you should be able to put in your things. So the other thing that what we call the stack very closely resembles the ROS concepts, with an enriched model. For example, when we talk about a node or a group of nodes, it may be something about a LiDAR or sensor controller driver or some navigation planning module. So it has parameters and uses and subscribes to topics, publishes something, it may have services, but it also needs an enrichment part, which, for example, defines the constraints on how it is packaged, what it depends on, both system and node dependencies. Plus, when we're doing the constraint programming, what I mean by the constraint programming is, if we deploy something onto a device, we have to validate it, and we have to make sure that it matches the constraints on the vehicle as opposed to what we're trying to deploy onto it. So those are some of the design constraints, and what came out of these are a Muto agent, which is basically a proxy that works with digital twins, and it's also a multiplexer. It redirects everything that's about adapting the ROS graph to something called a composer. Okay, that is what manages. But Muto agent also works with the ROS runtime. For example, I can change something on my vehicle's twin that I want to do telemetry on some of the data that's flowing on the ROS topics. These are not probably meant for telemetry. They are going on, 40 hertz with gigabytes of data. But I can specify, send me, a mapping of that data every 15 seconds onto the twin. So this gives me a sort of a simple digital twin-driven interface to publish telemetry onto the cloud. What we call the managed stack is basically, it can be any algorithm. It can be AutoVer, F110, whatever you're building, etc. As long as you can sort of express it in terms of the simplified manifest, JSON, or the model that you can see, I can publish that using, again, twins. An agent picks it up, multiplexes it to the composer the constraint programming, and then takes it live. If you have to stop the car, of course, you need some node in that managed stack that understands that, okay, I have to stop the car in order to make that. So it's up to you. The adaptivity, again, is something very soft. For example, for us, one simple way of adapting a device could be through remote control. I can tell there can be a human operator sitting on the cloud watching the car, says, okay, it went out with that circuit, push a button, switch the algorithm. But you can also imagine, having some video processing. We are sort of experimenting with some of these. If you come out of one environment, can I detect the environment, basically scene detection, and I can attach each scene to a different stack and switch the algorithm. So you can have simplified adaptivity modules of this kind. Again, they get deployed onto the edge devices. We have, we are Eclipse fans, and there are lots of IoT technologies that are already in Eclipse that we can build on. So we use a lot of that scaffolding for us. For example, our digital twins are based on the Eclipse IoT Ditto project, which does answer a lot of the concerns about, how do I manage the security, who can do this, what is the device, and all that stuff, blah, blah part that I don't understand. That's built into the, I'm not a digital twin expert, so why not use what's already in Eclipse Ditto? So I think I took too much in our earlier slides, but let me just go over that. So the contextual adaptation is what we mean by that is all the metadata that are based on whatever your ontology is, basically are built into our stack definitions. And when Muto agent sends one of these to Composer decides whether it should instantiate the stack instance on that device and manages life cycle of each node on that graph. So it will make that stack instance live. And while you're doing this, of course, you have to answer a lot of the questions. For example, when I say there's a node, well, what if that node is not installed on that device? What do we do? Okay, so you have to answer a lot of the questions of, and to install that package, which has the node, what mechanism do I use? Is this based on containers? Well, then something else goes into play. Then I have to work with a privileged agent and composer that's running in a Docker or container on that device, or should I use Snap? There are no containers. And if that happens, what repository do I go to? So that definition, again, lives in the stack with the node enrichment. So it's a bit more than what you would see in a ROS launch XML or in the ROS2 scripts. Alexa? Okay. So again, this is an example of basically how you can build your metadata. You can come up with very different things. So versions, that can be a part of the constraints. Some of the safety attributes, okay, do not stop this module while the car is in motion. Okay, so these are the types of constraint programming and problems that you have to solve in the composer before you can take it alive. Again, this is not built into Eclipse Muto, but you can add that based on your ontology using a very simple syntax. How do we build our examples? And currently, this is our sort of a, if you like, methodology. We go to frontend or AutoVer. For example, if you go to GitLab AutoVer repositories, and I believe AutoVer is also interested in the Eclipse SDV and automotive projects, you can find, for example, their use cases built on valet parking. Built on ROS2. So we basically reverse engineer the ROS stack and create a stack definition from that one. And then we add metadata to that stack definition to define these constraints that are required to run that on a certain vehicle. We did the similar thing, for example, we do the similar thing for F110 examples. If you are a fan of that, you can go to, for example, f110.org, then you'll find many repositories from very different years of running that competition from different universities. These are ROS-based solutions. We reverse engineer stack definitions from that one for each year. So you can run different circuits, which they have a very good documentation, lots of data sets where you can test these things. So from that one, when you go into stack adaptation, you have to write this adapter, which is basically a ROS module which listens to the stack and the twin channels, and it can publish commands again on the stack channel on the ROS device, which composer will pick up and decide if it should make the move. So it's basically up to you to build that. We're not providing any of that with Eclipse Muto. I think if you already heard me say this, there are two digital twins that we use. One of them is the stack definitions. These live in Eclipse Ditto. It has its own namespaces and versioning, and then the very, very natural place if you have JSON-based descriptions of a model. So stack lives on Ditto. Also, the vehicle definitions. One of the interesting things I want to explore in the, for example, the SDV common coding day, see what we can do with Velocitas and LIDA, and also I want to see, for example, CUXA, a vehicle abstraction layer, how can some of that metadata can be captured in the vehicle definitions there. So all that communication also adds into the Muto's architecture. The whole communication between the Ditto server and the Muto overlay on the edge device happens through Ditto. We use only MQTT for now. We haven't supported the other. So Muto agent picks up any comments, live or twin channels, messages, events from this specifically directed to a vehicle. And as I said, Muto agent then acts as a multiplexer. For example, if this is a ROS command, the agent may be able to handle this directly. It's basically a gateway for Ditto to get onto ROS. And for example, if I'm trying to do some telemetry from a ROS topic. Let's say there is, I don't know, LiDAR scan or I don't know, something else, the speed, you know, the control signals, whatever. I can send this back through the Ditto twin channel back to the vehicle as telemetry. But if it's something to do with the stack, it gets published onto the stack channel. This is basically your normal ROS topics. On ROS2, this is basically the DDS layer. Composer or anyone else can pick up this message. Now, there are some issues, of course. Our stack model is fairly rich, and anybody who's building these topic message descriptions on ROS, it has this very weird message description layer. So we're using basically we serialize the string and just publish it, and whoever picks it up has to turn it back. I'll skip some of these because I think we already talked about just examples of some of these pluggable extension modules for, you know, ROS and some of the ROS graph and ROS actions built in. But just sort of you have some idea of what we talk about the stack. As I said, we use Eclipse Ditto as a template to manage the vehicle and the stack. So they all look like these manifests. And when you publish them through different vehicles, the agent picks it up, multiplexes the composer, it does the graph rewriting, and then takes it live. We're also going to contribute a sandbox, which also has a Ditto sandbox. Well, I guess we can use the Ditto sandbox as the Ditto engine, but we will also have a fork of some of the F110 code with the stacks so that anyone can just take it up and run and try these things. I think it may also be a good space for preserving some of the good work done at the F110 group, because students do that work and then they just dump and leave. So there's some good work at GitHub, which doesn't get maintained. It's written for ROS. You have to take it to ROS too, things like that. So I think that would be a good place for maintaining that information. Muto Live UI is already, it has been on GitHub for a couple of years, and it's more, I will skip these micro front ends, you can go read about it, but the whole idea is that you build a user interface the way you would build with services, but have that user interface update while it's running. We tried this, and we took it to production in a couple of environments, and also transaction-heavy secure environments, and it works very well. So it currently supports JavaScript-based coding, so you write your user interface bits in JavaScript. It works with different packagers, and then it can be deployed onto different runtimes like mobile devices, web, Android Auto, CarPlay, whatever. Okay, and there's also this will all be moved on to the Muto space, but there's already some showcases that you can go build applications, whatever with this code. Thank you, and if there are no questions, I'm just.
That was the hottest presentation today, right?
It was all very well planned. There's this button here that you...
Okay. So I would say everyone who has a question right now in the room, get to Naci afterwards outside, right? And for the online stuff, our people, I said, by the way, we're still 70 people online. So it seems that we are onto something, that they spend 20 minutes waiting for us getting back to the room. That's not bad. And I'd ask them just to reach out to you directly.
Thank you.
Any questions? Okay. And yeah, thanks and sorry for... Yeah, it is what it is. Thank you very much.
Thank you, everybody.